and then you get like formulas for that. So we would like to do a similar study here, where we say like we would like to understand the change of the normal vector field, which is essentially the only information that we have. If you have the Gauss map, often oriented surface, then we can look at the change of that really as just as a map from the surface into R3, and that gives us a linear map from the changing vector space into the changing vector space of S2. Again, think of some subset of R3. It's a linear map. And because it's like an element of the changing space, so because n of p, the norm of this is always 1, you can take the derivative of it and see that the image of this tangent map for some arbitrary vector, if you take the dot product with the normal vector field, you always get 0, because that's essentially this formula here. So either you take the derivative of this by equivalently, you know that the tangent space of this of the sphere was exactly the vectors which are orthogonal to each other. So that's some important information. But if you have that information that this vector here, this vector is orthogonal to n again, that means that we have a vector in R3 which is orthogonal to the normal. That means it has to be tangent. So what this means is that we obtain a linear map. Eating a tangent vector, and it spits out a vector again in R3, but this happens to be again a tangent map. And then it's convention that like minus of that linear map, it's called the shape operator. And that's usually denoted by S. And in order to separate it from like S the surface, I make like small ticks at the end. That's a map, and usually by convention we take like to be minus of TPN. So like that's a linear map, but like by convention, we put a minus sign there, which will become apparent in a second. It's the linear map from so that's an important data, but essentially, as you see, it's the shape operator is just like giving you information about how the normal direction changes. So you have the normal direction of the surface, and because your surface is curved, so you have like the normal direction here, but you go to a different point, the normal direction changes a little bit, and the way that is the normal direction changes is given in terms of the shape operator. Measure change the Gaussian. And a different name, sometimes if you find that in books, it's also called the Weingarten map. Where Weingarten was a German mathematician, and like it's a funny name. It's like wine is like the wine, it's like to drink, and then garden is like the garden. So it's essentially like the garden of the wine. And it's in the following, it would be nice to get like an expression of the shape operator when we have an adapted frame. So E1, E2, E3 is an adapted frame on some open subset. Then, as we have seen, then E3 is essentially the same thing as N. So then we see that the shape operator, which is minus Tp of N in some direction V, which we can write as minus D E3 V, because it's essentially the same kind of like change of notation between T and D, because both of them are, you can think of them as functions in each component, and we can take, we have seen that these are equal for functions. So that's clear, and now we have to take like the structure equation, which was like written somewhere here, we can rewrite this expression as omega 1 3 in v direction here v1 plus omega 3 v 2 direction. Okay. So here we used also the anti-symmetry of omega. So you see these data that we had like up here, the omega 1 3 and omega 2 3 are now the same components as the shape operator. So there's nothing, it's essentially the same kind of information as the shape operator, or shape map. So it's just like a bit of a different way to record the same information, like the omega 1 2 and the omega 2 3 are now giving you like two different ways to write like the shape operator. Like a priori, if you can also see that as a definition, since this one is a linear map from TPS to TPS, and we know that the E1 and E2 are bases of TPS. You know that there has to be some elements here and some elements here that give you the shape operator evaluated on some vector. So you can see that also as a definition of these components. If you would not have known them before, then that would be one way to recover them, at least on the surface. And the shape operator is important because it's the analog of the B and the T, and the change of the B of the T that we had for curves. So shape operator is the analog of curvature and the torsion of the curve. So kappa and T tell you how T and B are changing in T direction. So the interesting thing is, like for curves, we have two vectors and we record the change of them in one direction. So that's why we get functions essentially. But S of P tells you how the normal vector field is changing in TPS in the two tangent direction. So for curves, we have essentially two independent vectors, namely T and B, and then the normal vector field is just like the product. So we have two vectors which might be able to change, but we only have like one direction in which we record the change, namely along the curve. That's not like we're not interested in how T and B would be changing outside of the curve. But for surfaces, we have essentially one vector only, but it can change in two directions. And that one is now recorded in the shape operator. But that's essentially the same kind of information, just that the type of change or like what changes has to be adapted that we live on the surface. Okay, to get some feeling about like the shape operator, I think it's helpful to look at some examples. The first example is the sphere. Maybe the plane is like the simplest one. So just like a flat plane, so that's like a sheet of paper in my hand. And that one has like clearly the normal vector field which is just orthogonal to the plane. So let's say the plane in xy direction being given by c equals to 0 has normal vector period, or normal period, given by n equals, just pointing in the c direction. And this one is clearly constant. So if I have the plane here, and I have the normal direction at two different points, and I compare how they change, you see like they are the same vector, so they don't change at all. So the normal direction is constant, so that means that the shape operator is always 0. Which makes also sense, because we would like to say like this, the plane is like the simplest example of like a flat thing, right? Like there should be no curvature. So if like the shape operator somehow records of like how much the object is curved, then like it would be a good answer that the plane is like flat. So that's that says that the plane is flat. That's no curvature. A little bit more interesting is the example of the sphere. The sphere of radius capital R has a Gauss map which points, the normal direction is just, if you have a sphere, then the normal direction to the sphere is like the vector that just points outwards in the radial direction. So that will be to each point we assign just a point, and that would be like just continue that. But we would like to normalize it, so we have to normalize it to have radius over R, so that we indeed get like a map that has like norm. That's the norm equals to 1. So if you now take the derivative Tp of n in the v direction. So what we do is we take some curve, by definition, v equals a curve at 0, that here is represented like this, and then we evaluate on that curve and change and take the derivative outside. So that's the definition of what it means to take the derivative of a map. So let's do that. Now we use the definition of n to get d over dt over 0 of c of t over r. Now we can take the derivative at 0, but at 0 the derivative of the curve is just like the vector v again. So what we end up with is that it's d over r. So that means that the shape operator, which is minus Tp of n, that's some vector, is just minus the vector over the radius. So there's like two observations. First, S of P does not depend on P. It only depends on the tangent vector that we plug in, but there's no P on our side here. It doesn't depend on the point. And that's also clear from, if you think about it, the sphere, there's no special point on the sphere. Like every point is like the same. So that's like essentially saying that it's like equivalent to the roundness of the sphere. So that means that every point on the sphere has the same curvature. That makes also a lot of sense. So there's not a special point that has like different kind of curvature. And a different observation is that S of P gets large, or maybe it gets small. Gets small if the radius goes to plus infinity. So if you have like a sphere that is really huge, then it's still curved, but the curvature is like very small, and that makes also sense. And similarly, if you have a small curvature, then this shape operator gets very large, with the minus sign. It gets very much negative. So so that's, we see that like SP is detects the curvature. So naturally, you would expect if you have two spheres of like different radii, then like the curvature of the sphere that has the bigger radii is like smaller than like a tightly curved object. So if you compare this small sphere with the big sphere, then you see like this one has a lot of curvature because it has to be tightly curved. So you see already, like the shape operator records some kind of the information about like the how much the sphere is curved. So we recorded nicely the shape operator, and you can see like two elements, like the P says like at which point the curvature is measured, and then here we see like some values here. The behavior of the shape operator at that point tells you then like the curvature around that point. But the problem is like that this one is really a map. It really maps one vector to another vector, and that will be like what we essentially talk about next time, is how to extract out of this relatively complicated operator some numbers, because we usually like numbers and not linear maps from two dimensions. So that will be discussed next time. But after the break, we talk a little bit about the shape operator in general and how it's related to what is called the first and second fundamental form. But first let's have 20 minutes break. So that means 35 we continue. We come to that in a second. It's just like convention. So that's not really a deeper reason. It's but there's one one lemma that is discussed afterwards. But it's really just accepted that there's some people who should do that. Yes. Yeah. But yeah, it's like I don't know. Like there's no real there's no real explanation of like why there need to be a minus sign. It's just like it's yeah, it's the definition. It's like you could also say like reformulate everything in just TPN, but for some reason people prefer the minus sign here, and it makes some formulas nicer, some others not. And that's not so yeah, you can either treat that as a definition or you have n to be a map now here. And then yeah, so like TP n b equals EDT and C of Q, where C of Q is. So that's that was the definition that we had like a few classes ago. Like the definition, if you have like n a map on the surface into R or into R3, and you just take that the definition. But yeah, you can also like so that dpn equals here, here. But that's essentially the definition of so it's like the same thing, but that's like just like last time we had that. So yeah. But like there's nothing else than n, right? Like it's just like it's like a function from S to R, away from R3 as in but like it's the same kind of. Okay, let's continue. For curves, we had like this nice analogy of like measuring the curvature of a curve by looking at like the acceleration of the curve, right? That was like if you sit in a roller coaster, and the roller coaster it has like tightly bent curves, then you notice a lot of acceleration which pressures you out of your seat in a normal direction. And something similar happens also for for curves, for surfaces, and that's recorded in the following lemma. It would be a detection of curvature by acceleration. So acceleration can only be measured from a curve. So let's suppose that we have a curve in S. Curve in S. Then you have the following formula, meaning that you take twice the derivative of the curve, that gives you the acceleration of the curve, and then you take the inner product with the normal direction. So there's nothing that guarantees you that the acceleration of the curve stays in the surface, right? But the only requirement is that the curve has to be in S, but the first derivative would be tangent to S, but the second derivative can be something. And then we take the inner product with the normal direction, and we get some number that measures the part of the acceleration in the normal direction. And this one is given as taking the inner product of the tangent direction with the shape operator evaluated at that point. So that really gives you the normal part of the curvature of the acceleration is measured by the shape operator. So that's the reason. And there was this question like, why do we have the minus sign in the definition of the shape operator? Essentially, you want this formula to hold. That would be one reason why there would be a minus sign. So if you just take like Tn here, then you would have a minus sign. So that's like, there's really no deeper reason in why we have the minus sign in front of the shape operator, except that some formulas look nicer if you absorb the minus sign in the shape operator instead of working with Tn. Okay, so that's the formula. So have a look at the proof. So if a curve is in S, then for all t's, the tangent vector has to be a tangent vector at the surface at that point that we take for all t's. Here. Because it's tangent, we know that C of t inner product of n C of t has to vanish because that's the normal direction. And then we take d of dt. Let's say t equals to 0 or to arbitrary time. And what we end up with is that the first element is 2 times the time derivative times n C of t plus, now we have the first element here, and we have to take the time derivative of the second part, but this one is just the tangent of n in the direction of C of t. And this one has to be, again, 0. And here we see that we recover minus the shape operator at the point C of t in the direction of the curve. And then just by reordering terms, you immediately get the equation that we wanted. So the upshot of this lemma is that for curves in S with a given velocity, velocity is say like v up here. Have the same acceleration in a normal direction. Namely, v times shape of orbit. So that's the surprising part of the lemma, is that like the left-hand side might depend on the curve. Like if you have two different curves and they have like the same velocity at the point, but like different like acceleration, then the second derivative would be different. But the surprising part is if you take the normal part of that acceleration, you end up with something that is completely determined by the shape of the surface and the first like speed, I mean like the first acceleration. So this left-hand side a priori, so this part here depends of course on the second like derivative of t. But like if you take the inner product with the normal, then you end up something that only depends on the first first derivative of the curve. So that's the surprising part of this proposition or lemma. And the way to see this is that this normal acceleration comes from the fact that the curve has to stay on the surface. And is determined by the geometry of the surface. So it's again like similar to the curves, is that like you can have like a curve in the surface, and because you're restricted on the surface, so for example if you have like a curve that like travels on a cylinder, because at each point it kind of wants to take off the cylinder, but like we want to restrict it again to be on the cylinder, so there should be some force that says, okay, curve, you stay on the cylinder, and so the curve experiences some kind of acceleration that pushes it back to the surface. So that's an acceleration in a normal direction, and that's given of course by the way like the surface is shaped and like how it's bent and curved. So that's like this analogy of the roller coaster, but for surfaces. So what you see here is like we now often encounter these kind of expressions where we have the shape operator, and it's given by some inner product with a different vector. So it's like that happens quite often that we now get something like that. So the idea is to give that new names so that we can study these objects a little bit better and independent. So that's the next definition. Is the first fundamental form is it's like it's spread is like 1, just the Roman 1. It eats a point and then 2 tangent vectors at that point. And what we want to do is we just take the inner product of both of these vectors. So that's just like a short way notation for the inner product. And the second fundamental form is a similar form where we say we take here and we take the inner product of the shape operator applied to the vector W for the same data. So both of these fundamental forms, both of them are each 2 vectors and gives you a number. And you can of course write the second fundamental form also in terms of the first one, which sometimes is handy. Honestly, there's not much value in the first fundamental form, at least for this course, because it's just the inner product of 2 vectors, which are linear tangent. So there's not much value here, but the important object is the second fundamental form, because it encodes the geometry in terms of the shape operator, and essentially it's like the same kind of information as the shape operator. And why I give the first fundamental form is because if I write down that this one is the second fundamental form, you obviously ask me what is the first fundamental form. So like the more important object is the second one. Maybe for now I record it, but I don't want to give the proof now. Maybe at some point I will do that. We have the following lemma, namely that these maps from TPS cross TPS into R are symmetric. So that means that if you change the position of the vectors, you get the same value back. For the first fundamental form, that's clear, because obviously if you take the inner product of 2 vectors, it doesn't matter in which order. For the second fundamental form, it's a bit more work to prove that.